So today we're going to be talking about functions and graphs, but not just functions and graphs. Actually, we're going to be talking about relation in graphs. And that's because all functions are relations, but it's not necessarily the case that all relations are functions, as we'll see in these guided notes. So let's start off with some definitions. A relation is a correspondence between two sets, or equivalently, it's a set of ordered pairs. And we'll see examples of this later on in our guided notes. And for this relation, for the two sets that make up this relation, we're going to call one of them the domain and one of them the range. So the domain is going to be the set that is all of the input values, which we also call the independent variable, and often we use x to represent that. The range of our relation is going to be the set that contains all of the output values for that relation, which we'll also call the dependent variable, which often is represented by the letter y. Now we'll get into certain types of relations, specific types of relations that we'll call functions. And we're going to label our functions using a certain notation called function notation that looks like this. And as I said, this is just function notation, where this f is actually the name of the function. It's the label that we can use to keep track of our functions, because you'll see that we'll actually be trying to deal with multiple functions at the same time pretty frequently. So you'll see different letters like F, G, H. You could put whatever letter you want there. But most of the time we'll see F, because F stands for function. So what exactly is a function? A function is a special relation. So a relation is a correspondence between two sets, my domain and my range. So a function is a special relation between my two sets, my two variables, such that to each value of the independent variable called the domain, as we defined above, there corresponds exactly one value of the dependent variable, commonly known as the range, and that exactly one value is what makes this a function. Is specifically a function, and not just a relation, but a special type of relation called a function. Now, looking at functions, we're going to see that there are four ways that we can represent functions: graphically, numerically, algebraically, and through words. Now, graphically just means points on a coordinate plane, where our domain is going to be graphed along the x-axis, and our range is going to be the set of values along the y-axis. Representing a function numerically simply means that we're going to be using tables or a set of ordered pairs to represent a function. Representing a function algebraically just means that we're going to be looking at equations with two variables, such as x and y. So for example, like y equals 2x plus 5, or you can use two other variables, whatever you want to put in their places, a and b, for example. And then representing a function in words is just describing how an input variable actually relates to an output variable, usually in a real-world sort of application. All right, now let's take a look at some examples of relations and functions. And we're going to, in these examples, determine whether each example is a relation or if it's specifically a function. So for letter A, we're going to look at this relation and determine whether or not it's a specific type of relation, a function, right? So a relation, as you remember, is either a correspondence between two sets, or it can be a set of ordered pairs. And in this case, we do have a set of ordered pairs, as we see, right? So now, in order to determine if this is a relation or specifically a function, we want to remember our definition of a function. And if we go back to the top, what was our definition of a function? Each value in the domain has to have exactly one matching value in the range, right? So let's look at our domain values of these ordered pairs. What are they? They're going to be 2, 3, -1, and 2, right? Now I see that my 2, it shows up twice, right? Here and here. So let's take a look at that first and see if that shows us anything weird, right? So I know that 2, it maps to a 5, right? Now, in order for this to be a function, it cannot map to anything else. All right, so I look over here at 2, and it's also mapping to a 3. So that means that this is not a function. And it is, in fact, just a relation because that value 2 maps to more than one value in the range. All right, let's look at part B. The area of a circle is a function of the radius. Well, it kind of gives it away there by saying that it is a function, right? So this is a function, but why is it a function? Well, let's write out the formula for the area of a circle, right? What is that? If you remember, the area of a circle is equal to pi times the radius of that circle squared, right? So for this to be a function, first let's determine, we know that this is a relation between the radius and the area, right? So what is my domain? My domain is going to be my r, my radius, right? And my range is going to be my output values, what I get when I plug in my r, I get my area. And now for this to be a function then, each value in my domain can only map to exactly one value in my range. Is that the case for this? If I plug in a value for r, does it always map to exactly one value for an area? Or can I get 2 answers for an area? No, I cannot get 2 answers for an area, right? When I plug in an r, there's always only one area for each radius of a circle, right? So this is a function. All right, now let's look at letter C. We have 2 sets here. We have a set of friends, and we have a set of birthdays for each one of those friends, right? Now we're going to pick one to be the independent variable and one to be the dependent variable, right? So my independent variable, I'm going to say in this case, will be my group of friends. I'll call that my set X. My dependent variable or birthdays, I'll call that my set Y. So I have a domain and a range. All right. Now, for this to be a function, each element of my domain can only map to exactly one element in the range. Right? Is that the case here? So if I look at Andy, does Andy have more than one birthday? No, he doesn't. He only has one birthday, right? So in this situation, this is indeed a function. Now, I'm going to turn that around. I'm going to actually flip these, and we're going to see what happens if we do that. So instead of my domain, or my independent variable, being my group of friends, and my dependent variable, or my range, being my birthdays, I'm going to flip-flop those. Now, my independent variable is birthdays, and my dependent variable, or my range, is going to be my group of friends. So now if I look at my domain, or my independent variable here, right, and I say, let's pick one, September 3rd. Does that map to more than one element of my range? Not September 3rd, right? But what if I look at April 13th? April 13th maps to Ruth Ann, and April 13th also maps to Sean. So it's mapping to 2 different elements of the range. So in this setup where my birthdays are my domain or my independent variables, right? This is actually not a function. This is simply a relation. Now let's take a look at some more examples, and I encourage you to try these on your own whenever you get to an example, just to kind of test your knowledge. And when you try things on your own, you're actually engaging actively with the material, and that's a much better way to learn than just sitting back and listening to a video. So I encourage you, whenever you feel up to it, to pause the video, give these examples a try, and then go back and see my responses and see if you were correct or not, or maybe I was incorrect. In which case, if you disagree with me, let me know, and I might come back and have to change a video. But moving on to example number 2, we want to still, as we did before, determine whether or not this is a relation or a function. So here we're going to look at representations of relations and functions graphically and numerically. So we're looking at graphs and tables, right? So when we look at part A, we're going to say, look at our domain, our x values, and our range, our y values, those 2 sets. And we're going to say, is there any x value in my domain that maps to more than one value in my range, or more than one y value? Well, if we look at -2, right? -2 maps to 8, but -2 also maps to 6. It's going to 2 different numbers in the range. So this is actually not a function. This is strictly a relation. Now let's look at letter B. We'll do the same things, except this is basically tabular format, right? Like in letter A, part A. we're going to look at the domain x and the range y, and we're going to say, is there any value of x that maps to more than one value of y? It doesn't look like there is, right? It looks like each value of x has only one arrow. It's only going to one y value, right? It's not going to two y values like that, right? So this is actually a function and not just a relation, but a special relation, a function. And lastly, what about part C? This is a graph, right? A graphical representation of a relation or a function. Is this a function? Well, to do the same thing, we're going to compare our domain and our range. So where's our domain in this case? Our domain is going to be the set of x values, right? So it's the set of all x values there on the x-axis. What's my range? Well, my range is going to be the set of all y values on the y-axis, right? Now, how do I compare the two? Well, I have to look at where the two intersect on my graph, right? So I look at the graph and I say, for example, when x is 1 here, what do I get from my y on my graph? I get -2, it looks like, right? So 1 is mapping to -2. Does 1 map to any other y value? No, it only goes to that one y value, right? What about, let's choose so far this is looking like a function. Let's choose another x value, say 2. When x is 2, it looks like I'm getting what for y? It looks like I'm getting about 1 for y there, right? Now, if I plug in 2 to this function, I get 1. Do I also get any other y values anywhere along that graph when x is 2? No, I only get 1, right? So it looks like each x value is mapping to exactly one y value, and that is the definition of a function. All right? And what I just did drawing those vertical lines in the graph, that's actually called the vertical line test to determine whether or not we have a graph of a function, which we'll see later on in our guided notes. Now moving on to function notation, now talking about these specific types of relations, functions. When we talk about functions, we use them so much in mathematics that we have to have certain notations for them, right? So we have this guy here called f of x. This represents a function f, labeled f, all right? This is read as f of x, as I've said, all right? Now we look at the next line. F, g, and h are used to name what? Functions, just different names for functions, because we'll be dealing often with more than one function at the same time. We can't name them all f of x because that would be confusing. So we'll give them different names. We'll give them f of x. We'll call one g of x, right? H of x. At some point, you might even see something like a of x. You can put really any letter or symbol that you want in the front, right? As long as it's something of x. But we'll normally see f, g, and h because we aren't going to be dealing with more than 3 functions at the same time for the most part. All right, now what does f of x actually mean? When we say f of x is equal to y, right? What I'm saying is I'm putting in a value of x into my domain, and then what I get out of that relation, of that function, is a value y. So f of x is always a y value. And f of x actually means the value of y at the number x. Is what x maps to in y. All right, and then f of 2 is equal to 9. What does that mean? All that means, graphically, is that the point 2, 9 is on my graph, because 2 is the x value, right, as we said here, and 9 is the y value. Now let's move down to example number 3, where we're actually evaluating functions. If you feel like you can answer these without watching me go through the video, then feel free to pause it and see if you can get the correct answers on your own and compare your answers to mine. But we're going to look at example number 3, and we're going to look at this function defined by f of x is equal to 2x squared minus 3x. And we're going to evaluate that function at different inputs, right? So we're going to look at, for example, letter A, we're going to evaluate the function f at the value 2 when x is 2. And now all that means is that wherever I see an x in my function, I'm going to replace that with a 2, and then I'm going to simplify and evaluate and come up with a final expression. So let's try that here for f of 2 in part A. So I'm plugging in 2 wherever I see an x in my function, and then I'm going to evaluate and simplify. And simplifying down, I can simplify it down to an answer of 2. So I know that when I plug in 2, f of 2, I get an answer of 2. What that means is that the point 2, comma 2 is on my graph. Now what about part B, where we have f of x plus f of 2? All that means that f of x plus f of 2, we're just going to substitute what we have, what we know, right? F of x is the same thing as 2x squared minus 3x, right? And f of 2, we've actually already found in part A. F of 2 is we evaluated to be 2. So plus 2. And then we have to simplify that, combine like terms, and evaluate that, right? Well, we cannot combine any more like terms, so that's actually going to be our final answer. Moving on to part C, where we have f of 2 of x. Well, what does that mean when I have this f of 2 of x, f of 2x? All that means is that where I see an x, just as I did before with this f of 2, right? Wherever I see an x in my f of x, I'm going to replace that with a 2x, which would look something like this. So all I did was put a 2x in place of x, right? That's how we start to evaluate the f of 2x. Now we just simplify and combine like terms, simplify down as much as we can, and evaluate to get our final expression, our final answer. And simplifying down as much as we can, we end up with 8x squared minus 6x. Now moving on to part D, f of x plus 2 is going to be the same thing. Instead of x in my function, f of x, I'm going to put it in an x plus 2. All right, and now I'm going to simplify as much as I can, combine like terms, and evaluate to get my answer. And simplifying down as much as I can, we get 2x squared plus 5x plus 2. Moving on to the rest of this example, part E, we have f of negative x. And now I'm going to rewrite the function f of x at the top of this page so we don't have to flip back to the prior page. So remember, this is our function, f of x is equal to 2x squared minus 3x. So f of negative x, remember, just means that instead of x in my f of x here, I'm going to put a negative x wherever I see x. All right, and that would look like this. And now we just simplify as much as possible, and what we arrive at will be our answer. And we end up at 2x squared plus 3x. Now looking at part F, we have negative f of x. Now in this case, the negative is on the outside of the f of x. What does that mean? I'm doing something to my function f of x. I'm negating it. I'm multiplying it by negative 1. So what happens when we do that? I negate the whole function f of x, right? I distribute that negative sign and simplify, and that'll be my answer. So I get negative 2x squared plus 3x. Now, what about part G? We have f of x plus h. Just like what we did before, we're going to plug in x plus h in place of our x and simplify as much as possible to get our answer. All right, I plug in the x plus h in place of my x and simplify as much as possible. It turns out that you cannot simplify very much. We get this long expression at the end for answer. All right, now let's move on to characteristics of a function. We've already talked about one of them, which is actually, in these 4 characteristics, is number 4. How an element of A, which is the domain, cannot be matched with 2 different elements in B, which is the range. Right, but we're going to look at 1, 2, and 3, which are some additional characteristics of a function that you should know. For number 1, we see that each element in A, remember A is our domain and B is our range, right? So each element in A has to be matched with an element in B. So you can't have someone in A who is all by himself and doesn't match with anyone. That breaks that function. It is not a function in that case. It's only a relation. For number 2, we have some elements in B may not be matched with any element in A. So that's kind of like number one, but now we're looking in the range, and we can say, well, there can be some lonely elements in the range. We can have some pieces in the range that don't match with anyone in the domain. That's okay for a function. But it's not okay, as we said in number one, for the opposite to be true. Okay? In number three, two or more elements in the domain may be matched with the same element in the range. So basically all that means is say pick something in your range, pick any one value in your range. That value can map to as many different values in your domain as possible. But as we see in this next number 4, and as we've talked about before, the opposite cannot be true. We can't just pick a value in the domain and have it match as many values in the range as possible. That would not be a function. But the opposite is true. For the range, any element in the range can match as many elements as possible in the domain. That's okay for a function. Okay, so we've covered each of the 4 characteristics of a function. You need to know these, okay? And now we're going to look at example number 4, which is a relation, not a specific, not a function, right? And we're going to see what the domain, range, and the relation as a set are. So for this relation, why is it not a function? Why is it only a relation, not specifically a function? Well, if we look at our 4 rules above, which one is it violating? It looks like set A here in my domain. I know that we cannot have any lonely elements of our domain, right? Is there anyone in our domain who doesn't have a friend in our range? Yes. This number 11 is all by himself in the domain. Therefore, this is not a function. Okay, this is only a relation. So what is the domain of this relation? Well, the domain is all of the independent variable values that we're using, right? So we're not using this 11 as we saw, so that's not going to be part of my domain. So my domain is only going to be the 6, 7, 8, 9, and 10. Well, what about the range? We're going to think along the same lines for the range. We look at only the values that we're using for our range, right? So that's going to be 52, 55, 59, 62, and 66. The other ones we can ignore for our range, right? And in case you haven't seen these brackets before, that's actually set notation. We use that to say this is a set of numbers, right? So my domain and range, remember, for a relation are sets. So my answers for those should be in set notation. All right, so then what is the relation? How can we describe the relation as a set? Well, it's going to be a set of ordered pairs, as we described at the beginning of our notes. All right, and this would be the set of my ordered pairs, right? So this is my relation as a set. So the 652, for example, I know that came from here where I say my 6 in my domain mapped to 52 in my range. Right, and so on and so forth. That's where I got those numbers, those sets of ordered pairs. So now what happens if I have a function, but I'm not told what the domain is, right? The domain is implied. So we're going to look at implied domain. All right, so if a function f is defined by an equation and no domain is specified, like I just said, you don't know you're not told what the domain is. In the domain, we can assume it's implied that it's the largest set of real numbers for which the value of f of x is a real number. So basically, it's going to be implied, if I'm not told explicitly up front what my domain, my x values are, then I can just assume that it's going to be the largest possible set of x values that give me a y value. That's the implied domain. All right, now contrary to that, we can have a specified domain, which is like example number 5, where they tell you exactly what the domain is, what your x values are going to be ahead of time. There's nothing implied about them. We know what they are, right? So we want to graph this function, y equals 2x minus 3, using the specified domain, right? So we're not going to look at all values of x, only the specified, these specified values of x, the set of x values. All right, so if I'm looking at my graph, usually when I graph, this is a line, right? Y equals 2x minus 3. So normally the line will go on forever from the left and to the right? But in this case, it's saying only look at these x values between -2 and 3. And that's including -2 and 3. That's less than or equal to, right? So if I graph this, I cannot go below -2 here, and I can't go above +3 here on my line. It's going to cut off my line, right? Because I'm only going to look at those domain values. So graphing this line, I know my y-intercept is -3, and my slope is 2, right? So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1, right? And so on. Down 2 over 1, down 2 over 1. And I get a line, but I cannot go past those points, those endpoints, all right? So I'm going to stop there, draw big old solid circles, because those solid circles represent the equal parts of the less than or equal to, all right? If that equal sign were not there, that equal part of the less than or equal to inequality, then I would draw an open circle and not fill it in. But that's not our case here. All right, now we're going to look at the tabular format for this function, for a function. In this case, it's going to be the function f of x is equal to x squared. We have a specified domain here. It's not implied because we're told what our x values are ahead of time, right? So this is for the specified domain of this function. We're going to evaluate this function at these x values to find the range that matches the domain values, right? So when I plug in -2, right, what is f of -2? F of -2, that just means I put in -2 here for x, right? That's going to be equal to -2 squared, which is equal to 4, right? Same thing for these other guys. I do -1 squared is +1. Plug in 0, f of 0, right, is equal to 0 squared, which is 0. What is f of √3? Is equal to the square root of 3 squared, right? What is that? That's just +3. And then same thing for this 2, square it, and I get 4. All right? Now for part C, we say we have, given the domain, we want to find the range for the mapping. That's basically exactly what we just did, except now our function is going to be the square root of x instead of x squared. And notice how we have g of x instead of f of x. It does not matter. They could have put an f of x here instead of a g of x, and it would be the same exact problem, right? But we're just using a different name for this function. All right, so then how do I find the range for each of these, for the specified domain here? Well, all I do is I take in each x value and I plug it into my function for x. All right, and then see what comes out. So let's take 0. What does that get? If I put in the square root of 0, I get 0, right? So 0 maps to 0. What about 1? I do the square root of 1, right? And I get 1. What about 2? What does it map to? I do the square root of 2. That's an irrational number, so we can't simplify that. We'll just leave it as the square root of 2. 3 is going to map to, similarly, an irrational number. You can't simplify the square root of 3, so we just leave it as the square root of 3. And 4, we plug in 4 to our function, and we get 2. All right, so now we're going to move on to implicit versus explicit form of a function. All right, so we can write a function in two different forms. What we've seen so far has all been explicit form. So that's like, for example, y equals 3x squared minus 2x plus 7. So the y, you solve for y essentially. The y is by itself. That's called explicit form. Now we also have implicit form, which is where your x and y's are basically mixed up. Your y is not solved for. It is not by itself on one side of the equation. So that'll be like 5x squared minus 2y cubed is equal to 4. So notice how my x's and y's are all on the same side, kind of mixed up, as opposed to the explicit form here, where my y is by itself on one side, right? That's the difference between implicit and explicit form.